Now that we've talked a bit about chemical reactions, we need to talk about equilibrium. Equilibrium is actually a state of balance. We can use this term to discuss any two opposing forces. In fact, we have some examples here. We're going to talk about first phase equilibrium. This is when two phases of matter are present at the same time. And a phase of matter, if you recall, are solid, liquid, and gas. So an example might be at 0 degrees Celsius, you have both ice and water. And if you could maintain that temperature, then you would continue to have both ice and water. It's not often that we stay at that temperature. That temperature is either dropping or increasing, but it's possible. Next, let's talk about solution equilibrium. That's when a solution is saturated with a precipitate. So if you were to look at a beaker containing that solution, you'd actually have some solid on the bottom. And what's happening is the actual molecules that are in the solid phase, they don't stay in the solid phase. Some will actually go back up into solution, and at the same time some that's in solution will go back as a solid. So that would be an example of a solution equilibrium. So you might have salt in water. All right, another example, and the one we're going to spend the most time talking about, is chemical equilibrium. And chemical equilibrium, it's important to understand that what's equal is the rate. So the rate of the forward reaction and the reverse reaction are equal. And we show that that's happening by having a double-headed arrow in the example. Take, for example, water, and we form that from H2 and O2. Yes, this is an unbalanced reaction, but the point I'm trying to make is about this right here, this double-headed arrow. If you see that, that means that the rate of the forward reaction is the same as the rate of the reverse. It doesn't mean that the concentrations of the reactants and the products are equal to each other. The concentration, and that's what these brackets mean, is constant. So it's unchanging because the rates are the same in either direction. So to list that, we would say that the concentration of the products and the reactants are constant. They're not equal, they're constant. They're going to remain the same. Because the reaction is occurring in both directions at the same rate, delta H will be 0. And then the reason for all of this is that the rate of the forward and reverse reactions are equal. I guess it should be rates of the forward and reverse. Sometimes there are some conditions where reactions can't be at equilibrium. And when we say they can't be, it's because they go to completion. An example would be if a gas is formed. And if that gas is formed in a system that is not closed, it will escape into the atmosphere. So that would go to completion. Another is if a precipitate is formed, which really what that means is if your product or one of your reactants at equilibrium is a solid, eventually everything will just become solid. It will form that. So that would also be an example of when it would go to completion. It wouldn't complete the reaction. So there was this guy named lechatelier who actually looked at equilibrium reactions and figured out how to predict what would happen. So lechatellier's principle says that when a reaction at equilibrium, well, that should be a reaction at equilibrium, is stressed, it will reach a new equilibrium. And we can actually predict how that will happen. Now, there's a few different stresses that can occur. We can actually have pressure changes. Now, pressure only affects gases. So if there's no gases in your reaction, then nothing will happen. And we'll talk about that one's kind of tricky. You could also change the temperature, because heat is either a reactant or a product at equilibrium, so that can actually shift the equilibrium of the reaction. We can also change concentration of something. Now we're going to use this term shift a lot, and whenever we refer to shift, what we're talking about is the side of the reaction that increases as a result of finding that new equilibrium. So let's do some examples. This first reaction we've actually given to you with heat written into the equation. Sometimes they'll give it to you and they won't put heat in there, but we can always look at table I to find delta H, and if delta H is negative, then heat's one of the products, like in this reaction. If it's positive, you would end up filling it in on the reactant side. We know this reaction is at equilibrium because of the double-headed arrow. Now, there's some tricks to making this so that you can always get the right answer, even if you don't necessarily understand what's happening. But let's do the first example and attempt to figure this out using logic. And then from there, I'll show you how to figure it out if it doesn't really make a whole lot of sense. So what they're saying in this first example is they're going to increase the nitrogen. So I'm going to actually draw right on my reaction here. If you want to do that, I would do it in pencil because we're going to do this several times and you'll want to be able to erase it. So I'm going to say this is my initial stress on the system. Now, it didn't have as much nitrogen previously, so it's going to want to try to get rid of that extra nitrogen. So to do that, it's going to react the nitrogen with the existing hydrogen. So the hydrogen is actually going to decrease in concentration, because as these two react, you're going to make more of the products. These things are actually going to increase. So it's going to attempt to adjust the nitrogen down by reacting it with hydrogen, thereby decreasing its concentration. And when it reacts with the hydrogen, it produces more of the products, which is why those concentrations increase. So to fill that in on our little chart underneath, our hydrogen went down and our ammonia and heat went up. And then to figure out the shift, which side of the reaction is increasing as a result, you're going to look at the up arrows, ignoring the initial stress, which is why when I put my initial stress, I circled it, so I know I'm not going to include that arrow when I determine my shift. And looking at the other arrows, the up arrows are all on the right, so my shift is going to be to the right. Okay, so we kind of went through that as if using logic. What I'd like to do now is do the next example using instead a trick that I've developed over time. So here's the trick, and I'm going to write this out at the top here. Same side opposite, which I would abbreviate SSO, opposite side same, which I would abbreviate OSS. So let's see how this works. This time I'm going to use blue. If I were to decrease the hydrogen, so my initial stress is to decrease the hydrogen, on the same side, that's using this here, the same side of the reaction arrow, here's my reaction arrow, the only thing that's on the same side is nitrogen. On the same side of the reaction arrow, the opposite thing, the opposite of the stress will happen. My stress was to decrease, so the opposite thing would be to decrease. So on the same side of the reaction arrow, the opposite thing is going to happen. Now to deal with the stuff on the opposite side, the same thing as our stress is going to happen. So on the opposite side of the reaction arrow, that's the right side, the same thing as our initial stress will happen. So these will actually decrease. Now we can fill in the second row here, what happened to nitrogen. It increased. Ammonia decreased. And so did the heat. So now ignoring our initial stress, which was our decrease in hydrogen, the side of the reaction arrow with the more up arrows is actually the only up arrow, and that's nitrogen. So our shift was to the left. Now I've started to make kind of a mess of this, and for whatever reason I can't erase, so I'm going to be doing the rest of the work on the lines for the problem. So we're going to talk about a decrease in ammonia. Here's ammonia. So we're going to decrease ammonia. And when we decrease ammonia, the same side, the opposite thing will happen. So heat is going to increase. All right. And then on the opposite side of the reaction arrow, so that would be our nitrogen and our hydrogen, the same thing is going to happen. And we said it was an initial decrease, so those will also be decreasing. Ignoring our initial stress, which was the decrease of the ammonia, the side with the up arrows is only the heat here, and that is the right side. Okay, same side, opposite, opposite side, same. All right, next one, we're going to increase the heat. So that's here on the right side. And it might actually help if you draw your little reaction arrow in here so you remember where that is. So if we are going to increase the heat on the same side of the reaction arrow, the opposite thing's going to happen. Same side, opposite. So ammonia will decrease. On the opposite side of the reaction arrow, so that's our ammonia and our hydrogen, the same thing's going to happen, which was an increase. This one's pretty obvious. The shift will be to the left. Now this last example is going to make this all even harder. When you are dealing with pressure, you can't use same side, opposite, opposite side, same. Essentially, when you're dealing with pressure, the only way it could make a difference is if you have at least one gas in your reaction. We actually have 3 gases in our reaction. And what you're going to need to do is count up your moles of gases on each side of the reaction arrow. So on the left here, we have, even though it's not written, there's 1 mole of this and 3 moles of this. So we have 4 moles of gas over here. And on the right side of the reaction arrow, heat isn't a gas, but this is a gas, and we have 2 moles of that. So I'm going to put a 2 here like this. Now, what will happen when you increase the pressure is when you have more moles, they're going to, the side that has more moles, they're going to collide with each other more, and as a result, they're going to end up reacting with each other to form the stuff on the opposite side of the reaction arrow. Since nitrogen and hydrogen are on the left and you have more moles of that stuff, they're going to react with each other more, and as a result they're going to decrease, and they'll end up producing more of this stuff on this side as they hit each other. So we are going to decrease the hydrogen and the nitrogen, but we're going to increase the stuff on the right side, so that's going to be a shift to the right. Another way to look at that, we say more P, less G. And what that means is when you have more pressure, the side with less gas will actually increase. And then the opposite is true as well. If you had a lower pressure, then the side with more gas would increase. More P, less G. All right, we have another example here, same reaction. If we were to decrease the heat, so if we were to lower the heat, on the same side of the reaction arrow, the opposite thing's going to happen. So this would go up. And on the opposite side of the reaction arrow, the same thing will happen. So those will go down. Since our reaction arrow is here, that means our shift must be to the right, because our up arrow is on the right. Let's try some more examples. New equation, a little less messy. The first question is about pressure. So before you can even answer anything, you need to check to make sure you have at least one gas in your reaction. This is a solid, this is a solid, oh, there's a gas. So something will happen when you change the pressure. So we're going to add up just the moles of gas. And on the left side, there are 0 moles of gas. And on the right side, we have 3 moles of gas. So when we have more P, I'm going to write this again, more P, increase the pressure, it's the side with less moles of gas, less G. So the side with less moles of gas is going to be the NaClO3, that's the only thing over there, and everything else decrease. Since our reaction arrow is here, the shift is to the left. Next one, we're going to decrease the heat. I'm going to use my colors again. If I decrease my heat, that's my initial stress. On the same side of the reaction arrow, the opposite thing's going to happen. And on the opposite side, the same thing's going to happen. So to fill that in down below, our shift is going to be, because my reaction arrow is here, to the right. And then to remove O2, really they're saying decrease O2. So let me do that with blue. I'll do it below. So we're going to decrease this. On the same side of the reaction arrow, opposite thing's going to happen. On the opposite side of the reaction arrow, the same thing is going to happen. So this will decrease, increase, and increase. And since our reaction arrow is really right here, that's a shift to the right. This stuff isn't easy. We're going to do more practice in class, so don't beat yourself up if you're not getting it. But I think that these mnemonics, more P, less G, and then up here, same side opposite, opposite side same, that stuff's going to help you the most.